The pore pressure prediction approaches typically used in industry, like Bowers or Eaton, are based on the vertical effective stress method. However, the fundamental assumption of uniaxial strain is not always appropriate for more complex geological settings such as near salt diapirs. The full effective stress or FES method seeks to address this issue by accounting for the additional contribution of both lateral and shear strains. The FES method follows the form of the Bowers equation but invokes 4 additional input parameters such that pore pressure calculation is conducted in terms of the full effective stress tensor. Stress perturbations and interactions around complex 3-dimensional salt structures are rarely known a priori, and hence this information is extracted from a static geomechanical model. For further detail on the FES method, refer to Heydari, Nikolinaku and Fleming's 2018 in Geophysics. 2 case studies involving stress and pore pressure prediction around offshore salt structures will now be presented. The first is from the Gulf of Mexico, the second from the Tafalla Basin near the Canary Islands. Both have been validated by post-drill data with encouraging results. For more comprehensive accounts of these studies, refer to our conference papers at ARMA and EAG 2020. Rotating 3D perspectives of the Gulf of Mexico model are shown. On the left, contours are of FES pore pressure normalized by the VES pore pressure. On the right, contours are of the ratio of deviatoric stress to effective mean stress. Hot colours indicate areas with more deviatoric stress and of higher FES pore pressure. Generally, more deviatoric stress is seen above the crests of the subsiding salt canopies, while more isotropic stress arises in the centre of the mini-basins, compressed by lateral creep. Significantly elevated FES pore pressure is predicted in the vicinity of the salt structures where mean stress and/or deviatoric stress is high. 2D cross-sections through the model are now shown with the same contours, along with 2 synthetic well trajectories. Well 1 sees more isotropic stress due to its position within a compressed mini-basin, and hence FES pressure is generally less than 10% higher than VES. Well 2, which penetrates a salt canopy, sees shallow dilation accompanied by more deviatoric stress, but compaction and more isotropic stress below the tongue. FES pressure is almost 15% higher than VES in the shallow section, but less than 10% higher at depth. Note that the deviatoric ratio alone does not tell the full story when comparing FES with VES pressure. The dotted lines plot the MES to VES ratio, which accounts for mean stress but not shear. The influence of shear stress alone on predicted pressure is therefore highlighted by the difference between the dotted and solid lines. A field-wide 3D perspective of the Tafalla Basin model is now shown with contours of deviatoric stress ratio. Note that here the sediment was initialized with a ratio of between 0.2 and 0.3 with variation due to lithology. A similar picture is revealed with more deviatoric stress states above subsiding salt canopies and more isotropic stress states within the mini-basin. The Sandia well is located above a north-south trending crest of a shallow salt diaper. Along the well, predicted FES pressure becomes progressively larger with depth, reaching a maximum of about 10% at the base of the well. This tracks the increase in deviatoric stress ratio and again highlights the role of shear stress in the FES pore pressure prediction method. In both case studies, minimum stress and pore pressure predictions were validated against a range of post-drill data. The graph on the left is from a recently drilled exploratory well in the Gulf of Mexico. Axis scales have been removed for anonymity. The graphs on the right are from the Sandia well in the Tafalla Basin. In both cases, the MES method is also shown along with the VES and FES pore pressure predictions. Model results correlate very well with minimum stress observations. The MES and FES methods predict elevated pore pressure relative to the VES method, and the range in predicted pore pressures compares well with the spread in measured data. The modelling was of value in informing operational decision-making, such as setting of casing depth. Predictions of minimum stress were considered reliable, and the model continues to be used during field development for well planning and drilling risk assessment. the models can be refined as more data becomes available. At Sandia, the model successfully predicted the observed narrowing of the drilling window in the deeper part of the well and the shallow uniaxial conditions. These conditions would not have been anticipated without the geomechanical modelling. The results support the notion that lateral and shear strains in the vicinity of the salt may contribute to elevated pore pressure.